Next we have Richard Cartwright, who is in character. He's here from the 1870s, maybe the 1860s. See if you can tell the difference here. He's the CTO and founder of Streampunk Media, and he is talking on an interesting topic. You'll enjoy this. Internet of Things architecture for cloud-fit pro media workflows. Richard, take it away.
Yeah, good, thank you. So, what am I going to be talking about on this topic? So I'll give you some background and motivation behind the work that I've been doing and why we've been taking an Internet of Things approach in our work. What I mean by cloud-fit professional media workflow, which actually the previous speakers have already done an excellent job of defining, so thank you very much. What is virtualized in the context where I'm working? And what are issues that we've been discovering with trying to lift and shift SDI-type infrastructure into cloud-based environments? And also, we want to develop simple software that's easy to deploy and is cost-effective to use. So what do I mean by that? I'm going to present an alternative Internet of Things architecture. If we start from the internet and we go back to professional media production, where do we end up? So it allows us to build dynamic software infrastructure using a technique called reactive streams, which comes out of big data. That enables us to trade latency and bandwidth in what we're doing. And also the benefits of using an HTTPS-based transport for uncompressed media and some measurements we've done doing that in local area network and also on the cloud. The measurements I'm going to present come out of a proof of concept that I've been working on with the BBC in Northern Ireland, and I'll give some conclusions and next steps. Okay, so the background and motivation to this work. The audience are using an ever-increasing range of smart devices to consume our content. That is impacting, and we've already seen in a number of sessions throughout this conference, the way that we're going to consume content and the kind of content that we're going to produce. There's probably going to be a lot more, feedback and machine learning into personalization. That's going to increase the size of the facility we need to build and the agility that we need to have when we are building our infrastructure. The media and entertainment sector by itself is too small to grow this kind of scale and this kind of agility, so we need to rely on the architecture and tools of IT. So we need to bring in technology from cloud, we need to bring in technology from big data, we're going to be using software, and we're going to be needing to deploy that using the techniques of DevOps. And I believe that the Internet of Things, where we now have our heating controllers and our fridges, and our cars are going to be connected to the internet. Why not also our cameras and our microphones? Use the devices that we use internet-worked using the Internet of Things. We have a problem when we try and move to these kind of architectures. IT systems are inherently non-real time. We've been used to using installing systems in racks which have a real-time nature. And when we write software, we are trying to write, we're always trying to write software at in a higher level programming language, as simply as possible, abstracted away from that hardware, because that's how we write low-risk, cheap software. And then we can allow experts from companies who've got big pockets to be experts and do the optimization. And when we write that software, we achieve portability through using application programming interfaces that abstract us from underlying details. And in fact, we're trying as much as possible not to be that interested in the bits and packets at a low level, at a low engineering level. And in fact, when we move to the cloud, we really don't know what those cloud providers are doing in terms of providing us network infrastructure. So this is a story of a media geek. That's me. I do software. I work in media. Journey into the Internet of Things through experimentation, demonstration. I only write open source software. We've been working with uncompressed media predominantly and the transport that we've been doing of that media over HTTPS. So, the Internet of Things. What do I mean by the Internet of Things? Well, we've taken a tool from IBM. It's open source. It's called Node-RED. It's designed for wiring Twitter to your fridge or your iPhone to your heating or your light bulbs. And lots of people are using it with things like Raspberry Pis to automate functions in their homes, for example. What we've been doing is to add into Node-RED and you can do this on the fly, a set of media-specific capabilities. So we've added, for example, here a microphone, or the ability to bring in an MXF file or connect to an SDI card. So that's the capabilities down the left-hand side. You can load them in dynamically on the fly. And then from the top, you can wire together in a web browser, for example, a WAV file to a speaker that allows you to hear the sound inside the WAV file. Or maybe you've got an SDI input, you're going to put it through a converter into an encoder, get some H.264, keep a raw file copy of that for auditing purposes, and make an MPEG transport stream, take the audio through a separate route, keep an auditing copy of the raw audio that you received. So I'm just building little components of infrastructure by wiring that together in a web browser. The final example, I could take a live RTP stream and some content stored on a cloud store, put them into a software-only multi-viewer, and put them out on an SDI output. Okay, so just little bits of infrastructure, you build them, you hit deploy, and that computer is now running that infrastructure. From nothing to load the capability on the fly to running a little piece of infrastructure. At IBC, we demonstrated a smartphone-controlled vision mixer, the kind of thing that you can do with this environment. So we have a software-only vision mix, we had a live camera, we had an uncompressed pictures of some flowers from my garden, and there I am using my iPhone to control the level of the mix. So it's the kind of thing that, you know, because we've moved this into a software-only environment, that was running on a laptop sitting on the stand there, but it could equally, just as easily, have been running on a remote cloud server because those were internet protocols being used to do the control. The controller, interestingly, that's a DJ app called TouchOSC. DJs use it to control lighting effects and music in nightclubs. We just took that and we integrated that within half a day. It was really quite a simple thing to do. So what do I mean by cloud-fit professional media workflow? Well, we already had the characterizations of all the different clouds earlier from Microsoft, and that's really what I mean. Cloud fit is, we're enabled by tools and technologies to flexibly deploy either to our own data center, to a public cloud, to a co-location facility, or any combination of the above. For the creation and production of HD and UHD HDR material, that is compressed and uncompressed, maybe live streams that we're receiving, or we're doing some near live work, the ability to be able to transition those streams to and from file formats, including RAW file formats and MXF file formats, and also the ability to support 10-bit, 12-bit color, 422, 444 subsampling, and going forward floating point representations as well. So this is about applying these IoT technologies to the full quality professional media. In such a way that we can move that production around dynamically and build infrastructure on demand. To be able to have that flexibility, we really are talking about software only, that software is portable, that we're moving away from non-media specific technology in that case. Now, when we go to the cloud, the nature of that virtualized environment is being defined by that cloud provider. So I think there's many definitions of virtualized that I hear when I talk to different vendors, but the definition that I want is the one that is cloud. We have non-real-time IT systems, although when we say non-real-time, we don't mean slow. They are very, very fast. They are incredibly capable computers. We can map logical computers. What we want to do, what allows us, the power of the cloud, is we can map many logical computing instances to physical instances. And that's achieved by some form of time slicing of CPU, of network resource, and of storage. And that's often a proprietary aspect. That's what the cloud providers are differentiating themselves on. We also have an issue that modern computers, generally, they are multi-core. The new i7 server desktop chips just come out, and it's 6 cores instead of 4 cores as standard. And that's the sort of trend, is that we're seeing more cores, not necessarily faster clock speeds. So we need to write our applications to exploit concurrent processing. And that's achieved using through whatever programming language, that comes back to thread switching provided by the operating system. But threads get blocked because that's a resource sharing model. Also, we want to write our applications, and we heard in the first presentation in the workflow sessions part 1 about more and more people wanting to bring their own development. The kind of languages that we want to do that, C++ is not being taught in the universities anymore. The languages of web development are things like JavaScript and Python and Java. We want to use those modern programming languages, but they have garbage collectors because that simplifies programming. But garbage collectors slow and pause processing. So that means that if we have, when we're moving our media around, if we have constraints to microsecond interpacket arrival time, as some of the narrow band profiles for things like 2110 have, that's not going to be possible in software because my software just isn't on that often. So we will get bursting, and that's a problem if we're going to move to these virtualized environments. We also have a problem that in those environments, generally, there isn't good enough PTP or NTP clocks. You got Amazon, it doesn't have a PTP infrastructure, and it doesn't have GPS clocks that are providing a good enough PTP infrastructure. Yet. Well, we'll see. We also want to build simple software with the lowest friction that we can. And I have a concern about the costs of using uncompressed and high bandwidth streams, RTP streams, in a cloud environment. And here are some of them, and I can think of more. The requirement to use kernel bypass networking to be able to run these streams fast enough. I, as a developer, I do not want to have the TCP/IP stack inside my software, which is one of the proposed solutions there. Some solutions are bypassing virtualization at various points to do direct mappings into NICs. Well, that's not going to work in the cloud because Amazon, for example, provide their own NIC. You just don't know what your NIC actually is. Another way to overcome performance issues with UDP streams is to use specialist acceleration libraries like Windows Rio, but they require a level of expertise that's different from using the standard UDP library. Multicast support is definitely not universal and generally not supported on the cloud. So relying on multicast for scale is going to be a problem. If you look at the way the networks are architected inside Amazon, then that's not going to be coming anytime soon. So to overcome these issues, I've already seen a number of people producing some open source, some closed source specialist RTP to HTTP gateways so that they can go across the internet with RTP streams and overcome issues of network address translation and so on. But I think there's alternative technologies we could look at that look at things like cache and CDN. Adding FEC, if we want to go add reliability into our streams, if we're going over a slightly longer distance, it's a cost. We could perhaps be using TCP as an alternative. Then, some people say we need to use separate networks for media because that's the only way that we can guarantee our interpacket arrival times and so on. But I think that is just cost. So all these things are just cost points. And public key management, if we want to secure our streams, if you look at the SRTP spec, it actually says that that's for future work. Key rotation, security key rotation using RTP is an issue yet to be resolved. So, what's an alternative architecture? So if we take a computer, which is storage CPU, GPU, network, maybe it's got some ASI and SDI cards inside it to allow us to interface to existing infrastructure. We're adding in this concept of the Internet of Things capabilities that enable us to do media production. So funnels, which are inputs, valves, which do transformations, spouts, which are outputs, fittings, which do retiming or video editing type operations on streams, and gauges, which allow us to monitor what's going on. So we've got all those capabilities, which we wire together, as I showed you in the web browser earlier. We can either use the web browser or we can use a REST API to do that. But that's just configuring infrastructure on one computer. How do we scale that out to something a bit larger? So that one computer is actually part of a much bigger infrastructure. I might have lots of computers, and each computer is running many instances of my Internet of Things environment. But what I'm really doing is I'm starting at the top with a media workflow that I want to achieve and local policies that I have. I want to put those into an IT orchestration engine, allow that orchestration engine to spin up software-defined compute, software-defined networking, software-defined storage as required, to then deploy the Node-RED instances or the Internet of Things instances, then on the fly add in the capabilities, and then which have all been through source control, automated testing, and containerized in some way. And then those configure those up, do the wiring diagram such that I have streams running between these different computers, and then I have a running infrastructure. That running infrastructure is constantly sending monitoring statistics back to a time series database, and these things are very common in IT for monitoring, so I know very precisely whether I'm making it or not with any particular element of my infrastructure. And I might therefore be able to feed that back into my engine and spin up more resource, spin up more capability on the fly when I'm hitting particular limits. So if I use this architecture, the only thing that is media specific in this case is the elements of software. Everything else is coming from IT or from cloud infrastructure. We also use an approach called reactive streams. This means we don't have to distribute a clock everywhere. We're using timestamps and data-driven timing. We have the idea of reactive streams. I'll not go into it in too much detail here. Go and have a look at it afterwards. Google it, but it enables you to balance, make sure that producers don't overload consumers, and also enables you to perhaps introduce some asynchronous parallel processing at various stages in the pipeline. An example of that is, like if I had an SDI workflow where I have sources, I'm doing a mix, applying a filter, doing some graphics, and then going into an encode stage. If those are all currently separate devices interconnected with SDI, then some of that processing, DVE for example, is going to have a frame's worth of latency. And then the real-time nature of the SDI stream, I'm going to have to wait a frame before I get it into the next device. This is the same for if we move to RTP streams. With an Internet of Things architecture, I might be able to start considering moving aspects of that compute into the same computer, and then I don't have a real-time wait to move stuff down a pipeline. I'm just moving a pointer around. And although the actual processing at each stage is now takes significantly longer, overall, if I'm moving between the graphics processor and the encoder, I haven't got to wait real time for the stream to transfer. But I'm still configuring something up in a web browser in such a way that it looks like I'm building a pipeline. And then we have the opportunity to optimize by using more cores, by using GPUs, by other means to actually reduce the time per processing stage. So HTTPS transport, I mean, I do see this as complementary to 2110, an alternative that may well work well when we're inside cloud environments. And we wanted to try out and measure what moving uncompressed over HTTPS would be like. HTTP and TCP is not actually slow, but we do risk things like congestions and timeouts and slow starts. But we're using TCP on a LAN, not on a wide area network, so we don't really suffer from that. And so what I'm really talking about here is the cool TCP algorithms have been talked about at a lot of conferences like Microsoft Ignite and Google I/O. There's new TCP congestion algorithms that overcome some of the issues that TCP has had. And I'm talking about using adaptive bitrate style technologies where I'm pulling chunks of media, so I don't really suffer from timeouts because I know if I haven't received a frame fast enough. I just keep pulling frame after frame after frame. So the approach is to use HTTPS for encrypted media transport, so we get security. We're going to assume that the network is non-blocking, that it's over-provisioned, and that we've tweaked all our window size parameters so that it's appropriately set up. And we're going to use timestamps, so we don't have to worry about clocks, we don't have to worry about FEC, and we're really allowing the layer 7 technology to deal with the switch buffer issues. If the buffer overflows, then the TCP stack will deal with it. We use JavaScript to do the measurements, and you can look at the presentation afterwards, and that's open source. We did these measurements on Amazon, on some local HP servers, and also on some Intel Skull Canyon NUCs, just little computers like Mac Minis, but slightly more powerful. So what were those measurements? We measured HTTP and HTTPS. This is moving the first 15 frames. The first frame moved slower than real time over one of these streams, but from frame 2, 3, 4, 5, 6 and onwards, this is 1080i50 video, all the frames, and this is just 200 lines of JavaScript, all the frames were moving faster than real time. So once the socket is set up, we are moving media over HTTP faster than real time. So we've got a little bit of time in case we have some errors. I did the same with 720p 60. It takes a little bit longer to settle down. It does actually settle down, but I deliberately left the data showing that one of the frames there was slower than real time, but the stream does settle down, and that's shown by the following eye chart. So just take a few seconds on this. What we have is, what we measured was moving 1,000 frames as fast as possible. How long does that take? So at the very back of this picture, we've got real time, so 40 milliseconds for 1080i50, 16.6 milliseconds for 720p 60. We also moved quarter frame chunks around, so if we move quarter frame chunks around, we can potentially lower latency. And then we did measurements on AWS Linux, on AWS, that was on an R4 extra large 30 cents an hour server. And we did measurements locally in the lab on Windows machines. And in every case, the frames on average move significantly faster than real time. So 12 milliseconds for HTTPS, about 20 milliseconds, 12 milliseconds for HTTP, 20 milliseconds for HTTPS pull streams on Windows, and then about 21 milliseconds for HTTP, and I think it was 23, 24 milliseconds per frame HTTPS running in the cloud. But yes, fundamentally running faster than real time.
Just a point, you still have 2 more minutes more than the clock shows.
Okay, excellent. But that was using a single thread. So in every case, we are waiting for each frame to do a complete round trip of request, encrypt, decrypt, response. We can also move frames in parallel, so use 2 parallel threads, 3 parallel threads at the same time. And the measurements there show that moving to using 2 parallel threads was always an advantage. This is HTTP on Windows. This was HTTPS on Windows, so the encryption, decryption has an overhead. It's not quite such a benefit, but moving, sending 2 frames in parallel was always a significant performance improvement in aggregate. And because we can divide the frames into 4, then we can benefit there. We also measured what happens if, rather than moving frames as fast as possible, we move streams in real time. How do these scale in terms of one computer? So this was on the little Intel NUC. So number of parallel processes, one stream we were moving frames were taking about 20 milliseconds with HTTPS. But if we move 2 streams, 2 JavaScript processes, then it's about 23 milliseconds. Same for 3 streams, same for 4 streams. 5 streams is jumping up to 30 milliseconds on average. Oh, it's a 4-core computer. So, that's why we hit that limit. About 6, 7 streams, you've got a few frames are being delivered slower than real time, so you'd need bigger buffers, and that's not a good idea. But on a small sort of consumer-grade compute device, we can move 4 parallel uncompressed streams across the network. And this is processor load. I won't go into detail, but basically, the processor load was a relatively linear scale across the board, and HTTPS was only ever about a 2% overhead over HTTP. And we were doing the encryption, decryption on the CPU. So, implementation and further work. I've written up the protocol on GitHub. There's an implementation also on GitHub. We're going to expand the range of capabilities with things like ARJA cards. We've got Kona IP cards, so we can interface to the 2110 world. We're doing more with UHD, a broader range of effects, a broader range of file formats. So, in conclusion, can you lift and shift signal-based sort of specifications to non-real-time IT? I think that's an open question and one that we should consider. We know that evolving audience is going to bring massive scale. We know that the machine learning that we learned about on Monday is going to bring massive scale, and we're going to need to use internet platforms and cloud. So what happens, what I've been presenting is, let's start with internet technologies and introduce professional media using IT tools, development approaches, and deployment approaches. IoT provides us an architectural framework in which we can build these things, which is inherently secure, it's highly scalable, it's cloud fit, it's portable, and it enables us to use simple and popular programming languages like JavaScript. We can use techniques from big data like reactive streams to make optimal resource usage, and we have an opportunity to use HTTPS chunk-based transport to complement other transport protocols. And that seems to work really well on 10 gigabit and better networks, including in the cloud. So finally, why have we been doing this? Well, we've been doing this as part of a proof of concept, and hopefully the outputs of this proof of concept give you the ability to trial this approach, to take our measurements, to take our open source code at low risk, and hopefully that to demonstrate that it's cost effective at this point to embrace the stochastic nature of real-time IT, which relies on doing ongoing monitoring to make sure we're not falling off cliffs, rather than engineering the bits in the nanoseconds. So, thank you very much.
I have one question, and then Thomas Edwards has a question. Just so everybody's clear, and I think you made this point, that if you take SMPTE 2110, which is basically UDP, RTP, and you try to run it in the cloud with undefined quality of service on the networks, you will fail. So what Richard is showing us here is a way of using TCP. It has trade-offs too,
yeah.
right? And you've discussed some of those, so that's fair.
Yeah.
Thomas.
Yeah, Thomas Edwards, Fox. So what about using software-friendly mezzanine compression? Does that get you anything like VC2 or the upcoming JPEG XS?
So if you were using, there's sort of two aspects to that. So one is we can bring ourselves, we've been doing some work with AVCI actually, because that's the storage format that BBC happens to use. And obviously then that gets us back into a land where RTP is a much more thing that we can cope with, but HTTP works just as well. What's interesting is when you get to UHD, actually the bandwidths that you need in production start hitting the limits even with compressed streams. So we have been working with XAVC codecs at sort of 800 megabits, and then you start to need these sort of techniques as well.
People don't know this, but he's actually Queen Victoria's CTO.
Yes, that's right.
Yes. So thank you very much. Appreciate that. Thank you.